But everybody should see my screen now. Is it okay?
Yes.
Perfect. So welcome back after lunchtime for our presentation here. My colleagues and I will present the IEA-funded DHC project, Artificial Intelligence for Failure Detection, Forecasting of Heat Production, Heat Demand in District Heating Networks. And once more, the reminder concerning the recording. We don't need this anymore. Maybe I just start with showing the project partners. On the one hand side, it's our institute, Fraunhofer ISE in Germany, concerning the forecasting heat demand. The other part is done by CEA, the well-known CEA Lytton. Mathieu Vallier will present their part on the fault detection, and the person you probably don't know is Michael Steiber, who is head of the operation of the real district heating network in Liebenau. They run a small district heating network where we use data for putting up or mounting up the methods and also for the evaluation. And Simon Gertzhäuser is here with us. He's going to present the part on the heat forecasting with AI. I'm doing a very short introduction right now. And talking about the two parts or two topics which have been touched in this project. One is on the failure detection, as the title already shows, and the other one is on heat demand, and both approaches or both topics are using AI methods. The failure detection part was looking into a modeling of faults with simulation models of components of the DHN. The colleagues of CI were looking into the performance of machine learning algorithms, and they focused on failures which are not easily detected by other approaches like thermography or leak detection, because in these cases, obviously, the special benefit can be created. On the part of the forecasting, we analyzed several different methods of AI for forecasting, like the short-term memory network approach, LSTM, and the convolutional neural network, CNN, and also an older approach on ANN and LSI combination. We analyzed the potential of energy savings benefits by using these methods in the real network in Liebenau. And obviously, we did also the evaluation of the methods in the real district heating network in Liebenau. So now I hand over to Simon. It's your turn.
Yes, thank you.
Just let me see, sorry. No, okay.
So this is where my part starts. I'm Simon Gertzhäuser. I'm with the ISE now for 2 weeks full-time. And before I worked on this topic as a student researcher, yes. So the prediction of the future heat demand in the DHN, we wanted to do on the one hand for single consumers and also then for the total network, as Wolfgang already said, with artificial neural networks, with the goal in the end to provide supportive information for the network operation, which can on the one hand be for a human operator and in further steps maybe also for an automatic operation of the whole network. The data that we used to train, validate and test the models, as Wolfgang also already said, was recorded at the Stiftung Liebenau DHN in Mecklenburg in Germany. And we had roughly about 1 year of data at sampling rate of 15 minutes, which includes supply and return temperatures, flow rates, power and pressure meter readings for different buildings, and which also includes weather data and also weather forecast data from the online service MeteoBlue. Here you can see how the data looked like when it was inputted into the networks and also what the output then would be. So we have our current time step T, so the current time from which on we want to predict here. And from a past time horizon, we input the past heat demand of the network, and for weather information, ambient temperature and global horizontal irradiance. related with some temporal context that should catch some temporal reoccurring patterns or stuff like that. And for the weather data, we also have a future forecast for ambient temperature and global horizontal irradiance that is also added as more context information for the future part of the heat demand that we want to predict, also in combination with the temporal context information. We evaluated two different multi-step prediction approaches as we wanted to predict not only one time step into the future, but several time steps. We can do that by a single shot approach where we predict everything at once. So all the input goes into the model and all output time steps come out at once. And we can also use the autoregressive approach where we predict step by step. So we do one time step prediction and we use this prediction for the next one and for the next one and so on. As Wolfgang already said, we checked out two network architectures where one of them is the convolutional neural network. This is a network that is mainly used in image processing tasks as it applies something like 2D filters to data in its so-called convolutional layers. This is a little bit depicted at the bottom. So you see here like this short purple rectangle that is a 2D filter on the input data, creates new data point in the next layer and so on and so on. And in the end, we get the final output. On the other hand, we looked at the long short-term memory networks, which is one that is especially made for processing sequential data as it has recurrent connections and can, by that recurrent connections, maintain something like an internal state. So it has some kind of memory, as the name suggests, and is mainly used in natural language processing tasks. On the bottom here, you can see, oh, sorry. Yeah, maybe just back, so I have to say a few words for the architecture. Okay, you have the input, then the network where we have this recurrent connection, and final output layer creates the output. When you unfold this over time, you have something like the picture on the right, where you have the same LSTM network over and over again, and the recurring connection hands over its internal state to the next prediction step. Okay, now. Next slide, thank you. Coming to the results, what we then did in the end is a prediction of 12 steps into the future at a sampling rate of 1 hour, which is then 12 hours into the future. We used the autoregressive CNN as the, so to say, best working model, but in the end, all the models that we checked out showed nearly equal prediction performance, and also all of them work better than this a little bit older ANN plus LSI approach that Wolfgang mentioned before, where we have a linear system identification at first and predict the nonlinear parts with a simple recurrent neural network. We can capture trends and predict them well, but short peaks and fluctuations are quite hard to catch, as this is in most cases like this. And in these three pictures here, you can see some example predictions. So the blue line is always the true heat demand. The orange one is the prediction for these 12 hours into the future from the dashed line onwards. And for reference, you can also see in green the ambient temperature here. Yeah, as you can see, we can capture the trend, but these short peaks and fluctuations are really hard to get. In terms of numbers, what we can see on this slide is so on the sum of all office and residential buildings, so combination of most of the network, we get a mean absolute error of 4.2% in terms of, or with respect to the maximum Q dot that occurred during this 1 year of data. We thought it would be better to have this percentage values as the absolute values can vary a lot on different buildings and also in different network combinations. And the confidence intervals for 80 and 90% look like as follows. In 80% of the cases, we are -7 to +7% away from the real value, and in 90% from -9 to +10%. Here you can see the plot of the confidence intervals over the 12 prediction time steps. And the image basically shows us that we do not have any real loss in accuracy from the first prediction step compared to the last one. And as a, so to say, worst case comparison, here's the same network trained on individual greenhouses, which are not included here on the left for these metric values. And what you can see is that we're quite more worse here, quite worse, because basically the greenhouses are harder to predict, because I think, as far as I understood it, their rule is basically just when it's too cold, we heat, and they don't have something like this temporal reoccurring patterns as for office and residential buildings. And as a suggested implementation of all this, we can imagine something like a conventional control system as a basis, where the set temperature is corrected based on a heat demand forecast after some latency time. So we have the control set value, and the correction we calculate with a factor A that has to be determined then, multiplied with the difference of this Q dot of the latency time, which is the forecasted heat demand for this time in the future, and the current heat demand. Coming to the costs and benefits. So when we want to implement this, what we need is a PC or server for the continuous execution of the AI algorithm. We, of course, have to implement the software, and maybe we have to install additional sensors if they are not already existing. And in the case of the Stiftung Liebenau DHN, this was estimated up to 25,000 to 30,000 euros. On the other hand, what we get out as benefits is that we can include the thermal latency of the system into the control loop. We allow a reduction of temperature safety margins by having more information on what could happen in the future. And we can avoid overheating, which for this specific DHN would sum up to an estimated amount of 10,000 to 20,000 euros per year when overheating is avoided. And to conclude everything, recent AI approaches like the CNNs or LSTMs that we tried out here are able to predict the heat demand in a DHN with reasonable accuracy for 6 to 12 hours in advance. We can outperform older AI methods like this ANN plus LSI approach that Wolfgang talked about, and we can implement the AI forecasting in the DHN at quite low cost. And on the other hand, have a huge economic benefit that is very promising compared to the cost. For a detailed economic evaluation, extended simulation would be necessary, and in the ideal case, also an implementation of the AI forecasting into a real network would be very useful for further development, yes. And there are also questions on how we could implement something like a continuously learning algorithm that can adapt to new unseen situations. But this is something that has to be investigated in more depth first. Okay, so that's from my side. Now I think I hand over to Mathieu.
Mathieu, yes. Mathieu, are you ready? Perfect.
Yes, I am ready. Thank you. So yeah, I will continue with the part of the project which is dedicated to using AI and machine learning for fault detection. This will be an overview. So for some topics, it would be quite fast. So to leave you time for maybe questions, and of course can be discussed afterwards. So the question about fault detection in district heating system is first that they are often unnoticed, especially in the network and substations, as was, for example, pointed out by Gad and Werner in 2015. But some machine learning tools can help with that. The problem is with machine learning is usually that for this type of tasks, there is not data in enough quantity and quality. So what we worked at is to create a data set based on a simulation to have a clean baseline. So here now are the two examples or goals for the project, which will appear when somebody clicks on the on the mouse somewhere. Okay, so the okay, this maybe is the previous version. Okay, so the two goals will be to have a reference data set that we will use for studying fault detection, and we assess how this data set can be used and what is the quality of the generated data on some machine learning models. So that's what we will show you in a few minutes today. So here is the agenda for the presentation. I will talk first quickly about the way we simulated and generated the data, then a bit about the data set that we generated, and then a bit more on the results with the machine learning models before conclusion. Yes. So for the simulation model, as I mentioned, we simulate systems for with faults. What we did is we used mostly open source models and mostly Modelica models for this simulation. So as a first step, what we did, we selected suitable models from the literature. To do that, I won't go into details of the tables, but the first line shows you the steps. So first we identified model, we characterized the model features. So we did a systematic review of a number of models. Then we linked that with the possible most relevant faults, which we also studied in the different components we find in a district heating system. So that can be production components, the network itself, and substation and storage components. And then we are identifying some of we identified most suitable models for our purpose with some minor modifications. So in the table, there are underlined the models we chose, and all the details go into the report from the project, which will be public. Okay, so let's go to the next slide. So for each of this model, we perform simulation with the following principles. So at the center, we have the simulation model, in the Modelica model in this case, which we simulate using first. So the two important thing to remember here is that we used boundary condition profiles of 4 weeks with a time step of 1 hour, and we have generated 13 of them corresponding to 1 year, 52 weeks. So we have 13 different profiles. And for the simulation, we generate random fault profiles with a fault pattern, which is either a ramp or a step, with a randomly chosen start time and intensity. So we have a number of possible simulations that we can run. And we obtain results like on the right with, of course, different behavior, depending whether it's normal or faulty situation. So on the right here, we have the example, I think, on the fooling of a substation with the thermal heat, the conductance, which is in blue is the reference one, and the red is the one with a fault, just to give you an idea of the simulations. Okay, so we can go to the next part. So with that, we generated a full data set, so which I can show afterwards. The next part, the next slide. Yeah, so this was inverted, but okay, can you go to the next one? Okay, so this was just a table summarizing all the simulation that we did. Of course, I won't go into the details there, but we generated for several components with these profiles a number of random faults. So in total, we obtained about 3 million recorded instance for this data set. So this is all saved in a CSV file. And if you go one slide before, so I'm sorry, it was not the last version that I provided.
Sorry for that,
yeah. So this data set is available on the Kaggle platform, which is online and open. So we provided the data set with all the metadata that is required to use it. If you notice, I made a screen capture of the page with a usability index of 10 out of 10. So we tried to make it as usable as possible, and also included the IEA DHC logo with permission from the IEA DHC operating agent. And we have currently 4 datasets shared and also Jupyter notebooks for usage examples. So this is ready for you to be used by all other people. So now I go to the last part of the presentation regarding the machine learning models. Unfortunately, I won't be able to go much into details on that, but I will give you just an overview. Next slide. So first maybe the one before, just yeah. So just to recap, there are several possible applications of machine learning for fault detection and predictive maintenance. This classification is taken from a paper, but there are many others like this. Here we are focusing only on the classification and binary classification tasks, which are supervised machine learning. So mostly we are trying to detect with binary classification whether there is a fault or no fault in a specified simulation. And in terms of classification, we have several tasks. I will talk quickly about it afterwards. So yeah, next slide, please. Okay, so regarding binary classification, so in that case, we consider settings where we have simulations with either no fault or a given fault for a given component. So here we have four component and 5 type of faults. So there can be only one fault at a time. So it's rather easy task. What we can see that, and we tested several machine learning algorithms. What we can see is that for some of the tasks, especially the one related to efficiency, well, it's the machine learning models are picking up quite easily the faults, and it's more difficult with the task related to thermal losses, so heat losses in a boiler and insulation in a storage on the right. So of course there would be many details. I will just show you on the next slides a bit more detailed examples on a fault that can happen on the decrease of the COP of heat pump. So on the top we have an example with a strong decrease of the COP, so 84%. We can see that the COP, which is the gray line, is dropping. So this data is not available to the machine learning model, but from the other input data that we have, in that case, the temperatures, mostly the temperatures, it can guess and find quite accurately the presence of a fault. And on looking at the graphs, on the left, the orange points are depicting the fault detection probability, which are rather close to 0 at the beginning and go to 1 obviously when the fault is detected. And on the right, we have the fault detection after applying a filter to that. What is interesting is that on the second line, we have the same example with very small and progressive COP decrease of 3%. And still in that case, we can see that the model can pick and find that there is this fault. So the probability of a fault detection is increasing over time. And if we apply the filter, of course, at the beginning, we do not detect the fault, but after some time, we can spot a fault on that. So that's interesting to see that it's possible, although visually we would not be able to find it. Okay, so maybe I will, for the next slide. So the next slide is about multi-class classification. So just to mention that we consider 3 types of tasks. One is to distinguish between different faults on one component. The other task is to distinguish on several possible locations for network leaks. And we also have one about different possible location for unbalance in a solar thermal field, but I won't go into detail there because I guess we don't have time. So probably we need to skip the next slide, which was on the leaks, on the small example on the leaks, and we go to the conclusion. So for the goal of providing a reference data set, I've presented you Well, the overview of the dataset we have, how we simulated it, and how we provide it in the open data. And for the assessment of the data set, so we implemented several type of machine learning models. So you have the list in the presentation and the details also in the reports of the projects. And the results I mentioned already are some tasks are well easy to define, so are more difficult some are more difficult. And there can be interesting results for the leaks detection. Also, something I did not detail here is that we started to investigate how the models trained on the synthetic data set can transfer to a real system, which is a bit more complex to explain. But we're starting to do that, and we will yeah, provide some results on that step further on, maybe in other projects. Yes. Thank you.
Okay, thank you very much, Mathieu. Sorry for not having shown the very last version of the presentation. Simon, very much thank you very much to you as well. If there are any questions in the audience, please just come up with them. Was a bit dense, I guess.
So maybe a question from my side. Is there any final report to read? If you want to, let's say, to go through it a little bit more in detail, maybe a little bit slowly?
Yes, of course. We are just now creating the final report. And I guess it will be ready in autumn or so. I'm not sure exactly, but of course we do that. And this will be public afterwards on the IEA website.
Great.
Mm-hmm. May I ask one question?
Yeah, please.
So in the part that Simon was presenting, I was wondering if when you were considering the T set point based on the forecast and step before, so what kind of T set point were you referring to? Was associated to the aggregate, then heating demand, and then the set point for the district network, or if it's at the building level?
No, it's not at building level. It's the network level. I mean, there is already a control system in the DHN in Liebenau. So the set point is coming from this control, and
which is weather controlled.
Which is weather controlled, exactly.
Yeah. And so then essentially it would be like providing a more accurate assessment of what it would be the set point in the network.
Yeah, in fact, the point is that the current system is not taking into account really the latency time of the system. So this is sort of running right on the current demand, which is of course based on weather forecast, but also or outside temperature rather, but not really on the irradiation, for example. And the point is that there's about 1.5 to 2 hours of latency in the network. That means this is not really accounted for. And by using such an AI approach, you would much more be able to avoid especially overheating, which is a problem in this kind of, in the Liebenau district heating network. So that sometimes they're heating too much and they have to blow up or blow off, sorry, not blow up, blow off the vapor, because they produce too much energy. So
okay. Okay, thank you. Very
You're
interesting.
welcome.
Yeah, thank you for this very condensed but very nice and compact information. Would be great to integrate the slides into our documentation if it's okay for you. Then
yeah, no problem.
We just need the slides.
Yeah,
Marcos.
I would have a question on the first part on the forecasting. Regarding the MAI you have mentioned with 6.something%, I know adaptive regression based methods which achieve lower MAIs, even though they are much simpler. Did you compare it to any other state-of-the-art methods?
No, not really. You're
Okay.
completely right. I mean, we should really do that in the future to check how it works. But the aim was really to check if these kind of methods are really able to do sort of a robust forecasting, and regression analysis needs a lot of training as well, and or parameterization.
Not
So,
if you do
not-
them in an adaptive manner, then they are plug and play.
Yeah. No, I mean, you're right. It could be that a conventional method is even better. This is completely
Would it
right.
be
We didn't check that.
possible to provide the data, so the heat flows and the ambient temperatures?
Yeah, we can check that. I mean, you want to?
It would be interesting for me just
Yeah.
to check it with other methods, because then I get a better impression of this 6-something %.
Yeah, let's talk about that afterwards. How we could exchange the data.
Yeah, would be great, since we're a little bit over time, but still okay. Last question from Baghdad.
Yes, thank you, Dietrich. Yeah, a complementary question to Marcus. Exactly, that was also my question, because I was wondering that if you have a rough number of the features you've used for these ANN networks that you were using.
What do you mean by features?
The labels or the variables, the different variables that you were giving.
Okay.
For.
I mean, this was the different temperature in the network at about, how many were there? 30 or 40 pressure temperatures at different points of the network, and weather data input.
For the prediction models is only what is shown on one of the slides, so the second one of my part.
Yes.
Where is it? All right.
More. Still more.
Yeah. This one? No,
No,
sorry.
this one.
Yeah, exactly.
So it's basically these four. I mean, the time was encoded day of week, time of day, and day of year, I think, and then additionally global horizontal irradiance, ambient temperature, and heat demand.
Okay. Yeah. Thank you.
Okay, since contact data are available, you may have a discussion later. So thank you. So I'm just.
Thank you. You're welcome.
Yeah, I'm just stopping the video.